This presentation is about group 13 oxides. Group 13 elements react with oxygen at elevated temperatures to give a trivalent oxide. Boron is a non-metal of the group that reacts with oxygen to produce boric oxide, which is a weak acid, so it reacts great with a strong base. An example of this is equation 1, where it reacts with sodium hydroxide to produce sodium borate. The oxides of aluminum and gallium are amphoteric. Equation 2 is an example of aluminum oxide reacting with hydrofluoric acid, and equation 3 is an example of its reaction with a strong base. Gallium oxide, being amphoteric as well, works the same way, and indium oxide and thallium-3 oxide are basic, so they'll react with acids. As we can see the basic characteristic, it increases going down the group. Since group ionization energy decreases as we move down, the strength of the MO bond decreases, making it easier to cleave and thus resulting in the increased basic strength. Although these oxides are thermodynamically stable, this stability decreases as we move down the group, with aluminum oxide being the highest thermally oxide from the metals in the group, with a melting point of 2072 degrees Celsius. Arriving at thallium-3 oxide, which is very unstable. Thallium-3 oxide, also known as thallic oxide, decomposes approximately at 800 degrees Celsius, forming thallium-1 oxide plus some oxygen. This happens to thallium because as we go down the group, the tendency to form +1 ion increases due to the inert pair effect. Group 13 oxides are extensively used in the manufacturing of glass and glass coatings, but I want to focus on the application of aluminum oxide. A really valuable application is the formation of rubies and sapphires from aluminum oxide's crystalline form named corundum. The color depends on what type of impurities the aluminum oxide has. So for example, rubies have the red color because of chromium impurities, and sapphire get a green or blue color from iron and titanium impurities.